Today we'll be dealing with the interactions in classical radiations. So the basic Hamiltonian for classical radiations is H is equal to, as we know, kinetic energy P square by 2m plus the potentials. That means we have electric or magnetic field. It is represented as E phi of x minus E by mc into A dot P. Now what we do is we take up this field A. We work with the monochromatic field of the plane wave. So A is represented as 2A0 epsilon cap cos omega by c n dot x minus omega t. Let's put this all equations as 1 and this as equation 2. Here epsilon, cap epsilon and n cap, they represent the linear, this is linear polarization, and this represents the propagation direction of the wave. Again, now when we look into the equations, we have a term called cos term. This cos term can be written in terms of, cos theta is nothing but e raised to I theta plus e raised to minus I theta divided by 2. So here theta is omega by c n dot x minus omega t. So we can write the cos omega by c n dot x minus omega t as equal to e raised to, I'll just write it in the round part, e raised to I omega by c n dot x minus omega t, okay, plus e raised to minus I omega by c n dot x minus omega t, the whole divided by 2. So I'll just put it outside 1 by 2. So that is what we can write about cos terms. Therefore your A becomes this A equation, this I can put it as equation number 3. Substituting in equation 2 we have A is equal to 2A0 epsilon into, so here you have 2 here divided by 2 into e raised to I omega by c n dot x minus omega t plus e raised to minus I omega by c n dot x minus omega t. Okay. So that is my equation number 4. So you can substitute this equation 4 in your equation 1. So here you can see that the potential, actually we have H is equal to T plus B. So here we can just take up this potential minus E by mc into A dot P. So how will it look like when you substitute for A? So substituting 4 in the potential term, we have minus E by mc into A dot P. So that is like minus E by mc. Okay, you have this A0 here, this gets cancelled. you have A0, then the vector epsilon, then dot P, then this terms into e raised to I omega by C n dot x minus omega t plus e raised to minus I omega by C n dot x minus omega t. Now when you, this I'll just put it as equation number 5. Okay. Now just remember what you have learned for the harmonic perturbation. There we had two things, the absorption term and also the stimulated emission terms. Okay. And for absorption, we know that e raised to minus I omega t is responsible for the absorption term, whereas e raised to plus I omega t is responsible for the emission term, stimulated emission. So here we have seen that any one only will occur, either absorption or emission. So we need not consider both together, because that is not the process which is occurring. I think logically also we can understand that just one of the process will occur. So here we just consider the absorption case, and there we can you can recollect the harmonic perturbation. Potential V of t is given as V e raised to I omega t plus V dagger e raised to minus I omega t. So we are considering this V dagger e raised to minus omega t, which is responsible for the absorption case. So here we can see that V dagger e raised to minus I omega t. So here this, what we can see here is, this is the case. Okay. So e raised to minus I omega t, you can get it from here. So what is V dagger? So V dagger will be equal to E A0 by MC. Yeah, you have that minus term here again. E raised to I omega by C n dot x that times epsilon dot p. So we can just tell that if it is from n to I, from final state to the initial state, ni. So you can just put that bracket down there. And now we can just replicate what we have learned again. That is the transition probability Wi to n is nothing but, so I have told earlier, this you have to learn from what we have done before, so that you can write it directly. 2 pi by h cross e square by m square c square. That is again recollecting, we have written for the harmonic perturbation as 2 pi by h cross V dagger ni the modulus square. So that is what we are doing. So 2 pi by h cross we have written, then V dagger ni the whole square. So it is e square by mc square modulus of a0 square. Then what you have inside the bracket? So n to I. So we have e raised to I omega by c n dot x Okay. Then we have epsilon dot P, that modulus square, because that the whole thing becomes V dagger Ni. Then you have the delta term, delta En minus Ei minus H cross omega. Okay. So this you have to learn. Only if you know what is harmonic perturbation, you can do the classical interactions. Okay. So this I'll give it as equation number. Let's put this also equation number 6. This is 7. Now getting back, we want to find the absorption cross-section area. Okay. Absorption cross-section. It is given as equal to energy per unit time by whom? Absorbed by the atom and that we know it is from I to N divided by energy flux of the radiation field. So the energy flux is nothing but your energy per area per unit time. So in classical electromagnetic field, you have it as C U, which is equal to 1 by 2 pi omega square by C square, C modulus of A0 square. And energy density or energy per unit volume is equal to minus 1 by C dou by dou T of A. Putting everything together, we have absorption cross section, which is represented as sigma ABS is equal to, okay, energy is we have H cross omega. Then how much it is absorbed, that we have that is given with I to N. Okay, this one, that is 2 pi by H cross. Each one absorbs 2 pi by H cross, E square by M square C square, modulus of A0 square. All those things you have to write. Okay, so H cross omega 2 pi by H cross E square by M square C square, modulus of A0 square. Then you have that N e raised to I omega by C N dot X, then epsilon dot P I the whole square, then the delta function En minus Ei minus H cross omega, then divided by what you have, energy flux of radiation. So that is 1 by 2 pi, this is it. Okay, So I can put this as equation number. Okay, this I'll give it as definition as 8. This is 9. Okay, I substituting 9 here. That is 1 by 2 pi omega square by c into modulus of a0 square. Okay, you have a couple of cancellations. Okay, this 2 pi will go up and it will become 4 pi square. You have this h cross square. You have a omega here down, omega square down here, omega on top. So it becomes, an omega will be in the down part. Then I think when you simplify it, just do it for yourself and find out whether you are getting sigma ABS as equal to 4 pi square. That h cross I am retaining here itself by m square omega into e square by h cross c modulus e raised to I omega by c n dot x epsilon dot p. Okay, sorry, I have I modulus square delta En minus Ei minus h cross omega. So this is my absorption cross section. Okay, so this is a absorption cross section of a monochromatic light which we have considered monochromatic field of the plane wave. Okay, thank you all.